Okay, we're going to come back and we're going to do the first part of section 4 today. And this is, section 4 is called the Fundamental Theorem of Calculus. So if you can't tell from the name of the section, it's pretty important to calculus. So let's start off with a nice little warm-up. You can try this out on your own, pause the screen, and then come back. But yeah, here's the answers. It looks nice, doesn't it? All right. Okay, so again, what we are talking about today is called the Fundamental Theorem of Calculus, and this is the Fundamental Theorem of Calculus Part 1. This is the only part that we are going to be focusing on today. This was actually the result of that in-class activity at the end of the video from yesterday. What this is saying is if you take the derivative of an integral, differentiation and integration cancel each other out. So if f is continuous on the interval from a to b, then the function capital F of x is equal to the integral from a to x of f of t dt has a derivative at every point in a to b, and d capital F dx is equal to d dx of the integral from a to x of f of t dt, which is equal to f of x. So let me break that down for you. Oh wait, before we do that, you have three things that you have to look for. First, every continuous function, f is the derivative of some other function. Every continuous function has an antiderivative. The process of integration and differentiation are inverses of each other. So those are the direct results of the Fundamental Theorem of Calculus Part 1. Super de-duper important. So let's break down what the first fundamental theorem says. You are taking the derivative of an integral. So when you look at a problem, you should have differentiation symbol in front of integration symbol. First thing we look for. Next thing we look for, the derivative variable matches the upper limit of the integration. So again, the differentiation variable, what we're differentiating with respect to, has to match this guy right up here. Notice how they're both x's. Sweet. Next, the lower limit has to be a constant. So we're looking derivative of an integral, variable matches the upper limit. The lower limit is a constant. Then we replace whatever the variable is inside of the integral with whatever that upper limit was. In this case, we took ddx of the integral from something to x, so we replaced the t with an x. So let's use this and apply it. We're going to apply the Fundamental Theorem of Calculus Part 1 to these two problems. So looking here, you can run through that checklist that you have to run through to make sure the Fundamental Theorem of Calculus can be used here. We're taking the derivative of an integral. Both of these, yes. Does the variable of differentiation match the upper limit? That's an x, that's an x. Good. Wait, I tried to give a thumbs up. Good. X, x. Good. Lower limit constant. Well, negative pi. Oh, that's constant. 2. That is also a constant. So all we are going to do is replace the variable in the integrand with the upper limit. So this, the derivative of the integral from negative pi to x of sine of t dt is equal to sine of x. That's it. That's what the Fundamental Theorem of Calculus Part 1 is. Try out the second one. All right, cool. Again, variables match. Lower limit, constant. Sub. Done. That's the Fundamental Theorem of Calculus Part 1. I will remind you, the only thing we're doing today is the Fundamental Theorem of Calculus Part 1. So yeah, it really is that easy. Oh, but here's where we can run into some difficulty. Let's say the upper limit has not just the variable up there. So in this case, we're trying to find dy dx. we are trying to find d dx of the integral from negative pi to x squared of sine of t dt. All right, cool. So we run through our checklist. Are we taking the derivative of an integral? Yeah, that looks like derivative of an integral to me. Does the variable of differentiation match the upper limit? Kind of. The variable is still the same, but up here we've got f of x. Dang it, dang it, dang it. Is the lower limit constant? Yes. Okay, so we're kind of in the right location. We just need to figure out what we do when we take the derivative of a function with another function plugged into it. Oh my goodness, I hope you guys are saying the C word right now. And the C word I'm thinking about is chain. So what we're going to do here is we're going to take x squared and plug it in for t. We'll have sine of t squared, but not t squared. Why did I say t squared? We want to replace the x squared in there. I'm sorry. Sine of x squared. But we need to include our chain here. Since we have an f of x as our input here, we're going to multiply by d dx of x squared. And we could probably do d dx of x squared in our heads, right? I hope at this point you can. 2x sine of x squared. And I'm done. Oh, so we just made it harder, didn't we? But is it really that much more difficult? I mean, honestly, it is more difficult, but I don't think that adding that chain on there is too much more difficult. And you got it spelled out with the chain. Fill in the blank with the chain. So here's some problems. You can probably pause and check these out. I will point out that some of these answers that I have here, I've like distributed in or multiplied by whatever the chain is. Like here, I probably multiplied each term by x squared. Over here, I multiplied everything by 3. Do you have to do that? No. Down here, I definitely simplified a bunch of stuff, but do you have to? No. Does it make it better to look at? Absolutely. So there we have some straightforward fundamental theorem of calculus problems. Oh no. Here, we want to find dy dx, but the lower limit is variable. So here on this first one, I want to find dy dx, which means I want to find d dx of the integral from x to 5 of t sine t dt. So again, I run through my checklist. Am I taking the derivative of an integral? Yes, I am. I'm taking d dx of an integral. Good. Is the upper limit variable? No, but the lower limit is. Is the lower limit constant? No, but the upper limit is. If only I could switch those two limits, then I could actually do this. If only I had a strategy to switch the limits in a derivative. Oh wait, that was one of the properties from last class. We know, well, we're still doing d dx because we haven't done it yet. If we switch the limits to be 5 and x, this all of a sudden becomes a negative, right? Flip the limits, you get the negative value. I'm going to tell you, I'm doing a lot more steps up here than I would on my own paper, because right now, I probably wouldn't write down that I'm moving the negative out front, but I'm just doing that right now to emphasize a point. We now have the opposite of the derivative of the integral from 5 to x of t sine t dt. Now ignore the negative there. We just know that our answer is going to be negative. Are we taking the derivative of an integral? Yes. Does the variable of differentiation match the upper limit? Now it does. Is the lower limit constant? It is now. So now, this just becomes negative x sine x. So if your lower limit's variable and your upper limit's constant, just flippity flop them and take the opposite. I'm going to switch up colors so we can keep the problems separate. The second one's going to be in red. I'm making it color coded because I know I'm going to need more space for this one. I'm trying to take the derivative of the integral from x to x cubed of t sine t dt. Well, good news, it's the same exact integrand, right? Now again, I'm running through my my steps here. Number one, am I taking the derivative of an integral? Yes. Does the upper limit match the variable of differentiation? Well, here we see that we've got an f of x as our upper limit, but we know how to conquer that. We know to use chain. So I'ma go with a yes. Is the lower limit constant? Now here's where we can say, that's a no for me, dog. So what I need to do, I need to invent this so that I have a constant somewhere in there. So what we do is we again capitalize on one of our rules from last class. We change this to d dx of the quantity of the integral from, and we're just going to split this integral into two different integrals. It's going to be the integral from something to x cubed of t sine t plus the integral. Wait, no. I'm going to do this the other way around. I'm using that, the additivity one, the additivity rule, where you have like the integral from a to b plus the integral from b to c is equal to the integral from a to c. So I'm going to call this integral from x to something of t sine t dt plus the integral from something to x cubed of t sine t dt. So now all we have to do is figure out what number goes up here and down there. As long as it's the same number, we're going to be able to use the additivity. It doesn't matter what number you use. Use absolutely anything. You could call it A if you want to, and just say A is some sort of arbitrary constant in this case. I like to use just the number 0, just because it's the easiest one for me to write. And plus, I like writing out nothing up there. So now looking at this, I can see that this problem becomes the same thing as this problem. So my first term here is going to be the opposite of d dx of the integral from 0 to x of t sine t dt plus the derivative of the integral from 0 to x cubed of t. Why did I start spelling sine with an A? Sine t dt. So now again, on both of these, derivative of an integral, variables match, lower limit is constant. Cool. We just got to plug and chug. Here we're going to have negative x sine x plus x cubed sine of x cubed times the derivative of x cubed. There we have an answer. Probably not the best answer. We want to do some algebra just to make it look fancy. Personally, I'll put the 3x squared up front, make that whole term out front. 3x squared times x cubed is going to give me 3x to the 5th sine x cubed minus x sine x. That's probably the answer that would be on a multiple choice test. Sweet. There we go. I think I got some practice for you guys. Yeah, there it is, breaking it apart and showing you the exact steps spelled out word for word. And here's some practice problems. Maybe pause the screen, come back in a minute. Again, a lot of these are probably simplified. You don't have to simplify them if and you don't want to. Right. Now we are going to use the fundamental theorem of calculus part 1 to come up with a function that has this derivative. So again, when we started this out, we said fundamental theorem of calculus says if a function is continuous, then it has an antiderivative. Looking at this function here, we can see that cosine is continuous. We just know how it works. We have a polynomial in here. Polynomials are continuous. Since we have a composition of continuous functions, that is a continuous function. Since we have a continuous function, it must have an antiderivative. So the problem that we run into is, what is its antiderivative? Well, I don't feel like figuring out exactly what differentiates into cosine of 2x squared plus 3. So I have a cheat method to do this. What I can say here is my function, my f of x, is going to be equal to, I just say, the integral of that function. As long as my upper limit is x, when I take the derivative with respect to x, I'm going to slide that x back into my function if the interior looks exactly like this, except instead of an x, I use a t. So that guarantees that that function has a derivative that is cosine of 2x squared plus 3, doing all the stuff that we've done so far today. Now the problem that I see here is I have an antiderivative, so I have to have plus c. Remember, we have to remember the plus c on any antiderivative problem. Now, I also know that I have to have the lower limit, and my lower limit has to be constant. I can choose literally anything for my lower limit. However, there is one intelligent choice for my lower limit. My only intelligent choice for my lower limit is going to be my given x value. Whatever that x value is given here, I want to put it in down here. Now, why do I do that? I'm going to show you why. Because now, when I try to find f of 9, which, by the way, is equal to 2, it's going to be equal to the integral from 9. Since I'm talking about f of x, I'm going to replace my x with 9. This is not f of t, so I do not replace my t's with 9. This is going to be the integral from 9 to 9 of cosine of 2t squared plus 3 dt. From last class, we knew that to evaluate a definite integral, you really just have to evaluate the antiderivative at the upper and lower and take the difference there. Or, really, when I look at this, this is the integral from 9 to itself. We know that the integral from anything to itself is going to be 0. So this becomes 0 plus c is equal to 2. Any wild guesses what c is going to be? That's right, it's going to be 2. So all of this stuff becomes f of x is equal to the integral from 9 to x of cosine of 2t squared plus 3 dt plus 2. Do you have to go through all of these steps over here every single time? No, of course not. If I want to find a function that has a derivative of ln of 4x to the 9th minus 72x plus 3, where y equals 2 when x equals 3, all I'm going to do here is say y equals integral from x value 3 to x of ln of 4t to the 9th minus 72t plus 3 dt plus my y value. There we go. The easiest way to find a function that has a given derivative ever. You can do that. There are some times where you have to actually find the antiderivative, but this is nice if you don't feel like it. Cool? I hope so. All right, so I'm going to show you how to graph using one of these functions on your graphing calculator. And the steps to do this are in Exploration 1 on page 298. So you're going to need that, and you're also probably going to need a calculator. So there's two things that we're going to need for this next step. Sorry about jumping around there a whole bunch. I just wanted to make sure that you could see my calculator as good as possible while still seeing that that activity, the Exploration 1, again on page 298. So what you want to do first is graph in the standard viewing window just that capital F of X. So you're going to plug exactly what it says right into your, there we go, calculator. So y equals, and then just type it in. We know how to type in our integral symbol. Again, alpha window, fn int, 3 to x, tan x, tan t, dt. There we go. Let me graph it. Whoops, that's a bad graph. Just say graph it on the standard zoom window, so we won't want to go to standard zoom. And it's a thinking, and it's a thinking, and it's a thinking. You're gonna wait for a long time and not see anything. I mean, you could pause this, wait for half an hour, and it's still not gonna work. So I'm just gonna break that. Break it, all you have to do is hit the on button. See how my on button is highlighted in red? We should recall that the function tangent of x has vertical asymptotes. Yeah, it does. It looks like that bacon. I mean, if we forget that, let's turn this off and just look at tangent of x. All of our vertical asymptotes occur when sine is equal to 0, and that's at pi over 2, 3 pi over 2, 5 pi over 2. It's all the odd multiples of pi over 2. When we were looking at the fundamental theorem of calculus part 1, it required a function to be continuous. So when we're trying to graph over from -10 to 10, I'm looking at number 3. Your grapher begins by trying to find f of -10. F of -10, well, that's not really going to work because we have we have some discontinuities of tangent before we get to -10. It just does not work because of those discontinuities. So we're going to set our viewing window so that our calculator graphs only over the domain on the continuous branch of the tangent line, the function that contains the point 3, comma tangent of 3. So thinking about 3 is right around pi, right? So we know that if we graph this between pi over 2 and 3 pi over 2, hopefully we're going to get, oh, look at that. Now we can see the graph, as long as you make sure what you're graphing is continuous over that interval. What is the domain in step 4? Is it an open or closed interval? So the domain in step 4, what we used there was from pi over 2 to 3 pi over 2. It will be an open interval because we don't want to get to pi over 2 or 3 pi over 2 because that's where we have the discontinuity. The domain of capital F of x would be from pi over 2 to 3 pi over 2, exclusive of the endpoints. It is an open interval. Your calculator graphs over the closed interval, x min, x max. Find a viewing window that will give you a good look at the graph of f and produce the graph on your calculator. There we go. That's it. Looks like a squig. Wait a second. Wait a second. No. Gosh darn it. It's that one. Oh man, it still doesn't work. Ugh, we can't do pi over 2 to 3 pi over 2 because we have that discontinuity. Let's try a little bit more than 3 pi over 2. Maybe, or a little bit more than pi over 2. Maybe 1.6. And then a little bit less than 4.7, 4.5. Please work for me. Yeah, it's working. It's working awful slow, but it's still working. The thing that kind of stinks about graphing integrals like this, it will take forever, because what your calculator is doing is it's trying to do a Riemann sum for each individual point on the graph. It just takes some time. Go, 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 go. Oh, there we go. There is another exploration that you can try out if you want to. This will explain what the value of A does when you graph this. I will point out that if you are trying to get your grapher to go a little bit faster, you can manipulate the window. You can change your XRes to something higher. I believe I geeked out on the polar graphing to show you guys this last year, but if you make your XRes like 3, that means it's going to be calculating every 3 pixels. And you can see it graphs a little bit faster. It's going to be less accurate, but it's going to graph faster. I don't feel like leading you guys through that whole exploration. So there's your assignment. I will see you guys tomorrow.